When customers are designing a UPS or ESS system, either low power or high power, there is often a need for rapid prototyping. One of the ways how to rapidly test power components is by using evaluation boards. In this section, I would like to go in detail through onsemi double pulse tester evaluation boards for discretes, and later I would like to introduce our evaluation boards for gel-filled power modules. As the title might suggest, in this section I would like to go through the details of onsemi double pulse tester environment. The tester boards were created with intention to allow customers to purchase a relatively affordable and compact tester, which would allow them to easily benchmark different power components, especially silicon carbide. The tester should be used mainly for comparison purposes, to measure and compare the switching losses of different components on the same setup. You can scan the displayed QR codes, which take you to each board web page, which can give you ordering information, and mainly the application notes, which contain all the details, including the tester schematics, PCB layout, and bill of material. As you can see on the right side pictures, the system consists of the main board, which comes with assembled daughter card set. The daughter card PCB is designed for one of the 6 types of onsemi discrete packages for silicon carbide. Each package has its own dedicated PCB with layout perfectly suited to provide excellent switching performance. The other extension boards are available. One of them is the set of the daughter cards. This is basically a set of the PCBs which are assembled only with connection sockets and test pins. Power components should be soldered separately by user. Then, user can have a fair comparison setup. Same PCB with the same parasitics, but with different power components. The boards can be then plugged in and connected into the main board. I will explain more details about this concept in the next slides. Second extension board is the signal generator and hotplate board. These boards contain a controller stage and a hotplate board. It allows users to measure in elevated temperatures, such as 150 degrees Celsius. Next feature of the board is a built-in signal generator, which can be used instead of a laboratory signal generator and can generate pulse sequence and initiate the testing. On this slide, I would like to go through some details and features of the tester. The main board has a DC link, load inductor, and a gate driver stage. For the gate driver, we are using onsemi isolated gate driver NCD 57084, which is supplied by isolated gate voltage source. If user wants to change a preset VGS voltage, which is by default plus 18 minus 3 volts, we design the voltage source to be mountable on the sockets. Then, the voltage source can be swapped without soldering. On the market, there are at least 2 vendors offering different voltage versions of given DC-DC source. Or user can plug laboratory voltage source to the sockets. In regards of the gate resistor, there are separate gate turn-on and turn-off resistors. 2 resistor types can be used. Either a SMD resistor, which does need a soldering, but it benefits of low strain inductance, or through-hole type resistors can be mounted into pre-applied sockets without soldering. Next, nice feature of the board is that it comes with the assembled current transformer. This current transformer senses the device current around the daughter card pin and transforms it with a 1:10 ratio. This allows users to use standard oscilloscope, low current, high bandwidth probe. Then the current probe can be clamped directly on the main board. On the daughter card, it is possible to solder a MLCC capacitor, which can further reduce the stray inductance from approximately 30 nanohenries to lower values. Then, The current must be sensed directly on the device pins with, for example, Rogowski probe. Otherwise, a current distortion caused by the MLCC will be present. We are currently working on a daughter card setup, which will allow very high bandwidth current measurement. The next extension board is a hot plate and a signal generator. This board has a microcontroller and a display. By pushing controlling buttons, user can generate a sequence of pulses and control the switching sequence. With the hot plate attached, it can elevate the device temperature up to 175 degrees Celsius. User then can benchmark and compare hot and room temperature losses without exposing expensive laboratory equipment to high temperatures. In this section, I prepared a short video which gives a quick guide on how to operate the tester in the lab environment.
Hello, my name is Ondřej Pícha. I'm Applications Engineer in onsemi. Today I would like to introduce you our double pulse tester system for discrete components which we recently introduced. The purpose of the tester is that the user can rapidly test and verify switching losses of different discrete components and compare the losses also between different packages. The tester contains of a main board which is consisted of high voltage DC link, gate driver stage, current measurement and a load inductor. Then the tester comes with a daughter card system, and those daughter cards are pre-assembled with onsemi components. Then those daughter cards are meant to be inserted into the system, and then user can connect the oscilloscope, high voltage source, signal generator and measure the switching losses. Now I would like to explain extension boards which are available as an addition to the main board. First is a daughter card set available for a different and variety of packages. TO247, TO247 4-lead, SMD BPAC package, D2 PAC 7-lead, TOLL package and SMD 8x8. The boards come without the components assembled, and the purpose is that the user can solder and test and compare the devices which come with the tester with the different devices, such as with the different RDS on or devices coming from a different vendor. If user wants to measure in an elevated temperature, there is another extension board which is consisting of the control board and a hot plate. The hot plate can be then screwed attached to the daughter card. Then another feature of the board is that it contains a double pulse generator. Then the signal cable can be attached to the main board, and system can operate as a standalone without using a signal generator. Now I would like to explain the basic operation of the double pulse tester. First I prepared the main board. On the main board I connected the daughter card with D2 PAC 7 lead. On the main board I also connected the gate resistance of 10 ohms. Then on the daughter card I screwed the hot plate. For a signal generation I'm using the double pulse generator control board connected through this SMA cable. Then for oscilloscope sensing I'm using current probe attached here to the main board to sense the drain current. For the VDS voltage I'm using a high voltage differential probe connected directly on the daughter card. For the VGS voltage I'm using passive oscilloscope probe also connected directly to the daughter card. System is going to be operated at high voltage, therefore it's always recommended to use a protective safety cover. Let's turn the high voltage source on. Set the pulse width on the control board and push start button to generate the pulse. After some delay time, the pulse is generated. Then on the oscilloscope, we can see the blue curve is the gate voltage, the green curve is the drain current, and the magenta is the drain source voltage. Then switching losses can be extracted by using oscilloscope math functions and calculating the area of the power.
In the previous section, I explained evaluation board for discrete components. However, if customer wants to design a high-power UPS or ESS system, module is usually a preferred choice. Here on the slide, I have an overview of few modules evaluation boards which are available online. Again, by scanning of the QR codes, the link will take you to the web page of each board where you can find further details. For silicon carbide modules, we have available platform for half-bridge modules, where one board is hosting two half-bridge modules, a platform for full-bridge module, and a board for TNPC module. Let me explain few features of the board. Each of the board has an isolated gate driver stage, isolated gate voltage source, DC link, and power socket terminals on the bottom. The socket terminals allows to plug and connect different types of module, including those with press-fit pins. It could be either different RDS-on version from onsemi or devices coming from the other vendors. Also, as marked on the picture, module current can be sensed by using a Rogowski probe. The board shows recommended layout of power module as well as onsemi gate driver stage. The purpose of the board is that user can test either a double pulse test or run the boards in a continuous regime, as the design of the board allows high current operation. For example, if a customer who is designing an active front end for UPS can test the PCB with open loop operation and quickly determine steady state losses with a given module and check whether the module meets his requirement or not. In the previous section, I explained laboratory and hands-on evaluation platforms which are available. However, onsemi provides state-of-the-art simulation environments. In this section, I will briefly explain what tools we have and how the tools can be used either together with evaluation boards or standalone. onsemi offers two main tools for power electronic design. First is intuitive, web-based self-service PLECS model generator, or SSPMG. This platform enables engineers to create a custom, high-accuracy PLECS models for complex power electronic applications, which can help in early stage of the design process. Typical industry PLECS model don't always reflect the wide range of conditions the semiconductor components can be used in practice. For example, how the switching losses would be affected by using an induction motor as a load, or how the performance changes with the gate driver loop inductance and its PCB resistance. SSPMG capabilities are based on the onsemi physically scalable SPICE models, which are rooted in the semiconductor physics and the actual process variations, resulting in more accurate representation of the behavior in the circuit. With the addition of word electronic passive system components to SSPMG, the generated switching loss models achieve even higher accuracy than before. SSPMG loss models can be downloaded and then used on customer standalone simulation platforms or uploaded into onsemi industry leading Elite Power Simulator. The Elite Simulator provides a customer direct insights in how a circuit topology will perform across onsemi EliteSiC family products, Powered Range T10 MOSFETs, and Field Stop 7 IGBTs and IPMs. This webinar is not long enough to show you all the features and tricks of using the tools, but I strongly recommend you to check the instruction videos in the attached links. In the next slides, I will show few hints of how the tools could be used. In In this slide, I would like to show you how the evaluation board test data and the simulation data from the EliteSiC simulator web tools can be compared and used together. The main purpose of the web tool is that it should give a user a quick guide on the selection of the power components. However, its accuracy is also very good. For the test, I was using previously mentioned evaluation board in continuous operation with two 8 milliohm, two 1200 volt silicon carbide M3S half-bridge modules. The board was used in so-called back-to-back inverter rectifier regime. This means that one of the modules was used as the rectifier and the other was used as an inverter. And the energy was recirculating between the two, while the voltage source provided only the system losses. Tested where conditions showed below: power factor equals to 1 and -1 respectively, DC link voltage of 600 volts, output voltage of 200 volts, switching frequency of 80 kHz. During the test, the power losses of one module were measured. Then, the same 8 milliohm module was used in the simulation in the Elite Power Simulator, where the same conditions were used as for the laboratory testing. Then, the power losses data were extracted. As you can see on the data, the match between the two, measured and simulated, is pretty good. Here, it is in range of 15 to 20 watts, which is understandable as the simulator doesn't reflect the system losses happening on the driver stage, PCB conduction and eddy current losses, etc. For comparison, I added the measured data on the same PCB with a competitor module. As you can see, onsemi device performs better in this application as power losses per one module are lower. This is mainly due to the excellent switching speed of the M3S technology. Now, when we understand that there is a good correlation between the power losses from the simulator and the real measurement, we could use the simulator to estimate the losses with different conditions than we could measure. For example, tune the switching frequency, gate driver voltage, gate resistor, etc. Or we can simulate in conditions which the evaluation PCB doesn't allow due to its current limitations. For example, high current loads or elevated ambient temperatures. In this slide, I would like to show you comparison between the SSPMG tool and the double pulse tester I was showing you in the previous slides. Here, I am trying to show what is the effect of the parasitic components in the measurement circuit. By using the tester for the measurement of the switching losses, one can extract the dependency between the turn-off switching energy and the drain current, as shown on the chart with the orange line. When we compare the measured switching losses with the data coming from the default power simulator model, we can observe that the model marked with the black line is showing lower turn-off losses than the measurement. This is not necessarily wrong, as the model data could be extracted on a setup with much lower stray inductance. We can calculate the stray inductance of our setup. For example, we take the transistor turn-off event, where we measure the drain current DIDT and we measure also the voltage overshoot. Then we can calculate the whole stray inductance of the setup. This stray inductance, however, consists of the package stray inductance plus the PCB traces stray inductance. By measurement, we can easily determine what portion of stray inductance comes from the PCB and what is the contribution of the package. However, that is not important for us, as the SSPMG is using physical die model itself, and the parasitic components can be added separately. Then, we could insert the measured stray inductance into the SSPMG schematics to either of the positions shown by the yellow circles, and then we run the tool. The tool will generate a custom PLECS model which can be used in the PLECS standalone or in the online simulator. When we compare the custom model data with the measured data, we can observe that the switching losses rise significantly and now are matching the measured data better. This aligns with the theory, with higher overshoot is causing higher turn-off losses.